We come now to four very basic concepts in linear algebra: spanning sets, linearly independent sets, bases, and dimension. But before getting into the mathematical details, let me explain the motivation behind these concepts. The idea of unique identification of objects or unique representation of objects is important not only in mathematics but throughout life. It's everywhere. For example, credit card accounts are uniquely represented by a credit card number. Automobiles are uniquely represented by a VIN number. Products in a store are uniquely represented by a universal product code, also called a UPC. And even students at a university are uniquely represented by a student ID. In linear algebra, we want to provide unique representation for the vectors in a vector space. And we want to do it using linear combinations. In fact, we can often represent the vectors in an infinite vector space using linear combinations of only a finite number of vectors. Of course, as we have seen, uniqueness among linear combinations is not an achievable goal, so we have to settle for essential uniqueness. But that's actually only a very minor annoyance, really. It's not a big deal. The purpose of dimension, which is number 4 on our list, is to provide a measure of the size of a vector space. And we'll save any further discussion of that until after we've discussed the other 3 concepts. A spanning set for a subspace S of a vector space V provides representation for every vector in the subspace. Linear independence of a spanning set adds essential uniqueness to the representation. And a basis is simply a linearly independent spanning set, so it provides essentially unique representation, which is our goal, in one neat package. So let's look at these concepts. To explain the notion of a spanning set, we need a little bit of terminology. Let X be a non-empty subset of a vector space V. The linear span of X, often just called the span of X, and we will denote it by SPAN of X, or just X in angle brackets, these are common notations, is simply the set of all linear combinations of the vectors in X. So here is the definition in symbols. Span of X is the set of all linear combinations of the vectors in X. When X is a finite set, we may use either of these notations, which is quite common. I should mention that in the past, I've used this notation for the formal linear combinations of the vectors in X. But from now on, we're not treating linear combinations as formal expressions in general. There may be exceptions I'm not thinking of, but in general, a linear combination from now on is meant to represent a vector. So we evaluate the linear combinations to get a vector. It's not difficult at all to see that the span of X is a subspace of V. And so we're going to use these notations in place of the original notation that I used before, because we're thinking of the span, the set of linear combinations of the vectors in a set X as a subspace of a vector space. So we're thinking of each linear combination as a vector. The span of X is, in fact, the smallest subspace of the vector space that contains the set X. So here's a theorem. Let X be a non-empty subset of a vector space V. The span of X is the smallest subspace of V that contains the set X. Accordingly, it is called excuse me, the subspace spanned by X, or the subspace generated by X. And I'm going to leave it to you to show that the span of X is closed under linear combinations, and so is a subspace of V. The basic idea is simply that a linear combination of linear combinations is just a great big linear combination. As to the fact that the span is the smallest subspace of V that contains X, that's pretty simple. If T is any subspace of V that contains X, then T is closed under linear combinations because it's a subspace, and therefore it contains all the linear combinations of the vectors in X. In other words, it contains the span of X. So the span of X is contained in every subspace that contains X. Therefore, the span of X is the smallest subspace that contains X. Now, a set of vectors X in a vector space V is said to be a spanning set for a subspace, or it's said to generate or span the subspace if, I guess that's what I'm saying, if the span of X is equal to S. I want to make a brief comment about this definition of the span of X as the set of all linear combinations of vectors in X. Some authors define the span of X not as a set of linear combinations of vectors in X, but rather simply as the smallest subspace containing X. And we know now these two are equivalent. The other definition, as the smallest subspace, actually has considerable merit. For one thing, it generalizes to other algebraic structures, and therefore it's more in the spirit of abstract algebra. Our definition is specific to vector spaces, actually also applies to modules, but we don't need to worry about that. But I chose the definition, even the definition I gave, even though I prefer the other one really, because it relates more directly to the purpose at hand, and that is to provide unambiguous representation of vectors via linear combinations. The xy plane P in R3 has this spanning set, two vectors. So we can write, excuse me, I'm having a little problem today. P is the subspace spanned by these two vectors. This notation is okay, so is this. In the first notation, I dropped the curly braces because I thought it was a little bit easier to read, but I kept them in the second notation. The plane is also spanned by this set of three vectors. So it is the linear span of these three vectors. In general, subspaces will have many spanning sets, infinitely many spanning sets, in fact. So long as the field, the base field is infinite, like the real numbers or complex numbers, there are going to be infinitely many spanning sets, except for the trivial subspace, which is only spanned by the zero vector. The subspace E of the polynomial space, f square bracket x, consisting of the even polynomials, is the linear span of the even powers of x. So that looks like this. This is also a spanning set. So you could, in fact, define a polynomial as even if it is in the linear span of these vectors or these polynomials. That's not generally how it's done. It's generally done this way, by saying that p of x equals p of negative x for all x. But this is a definition that works when you think of polynomials as functions. If you're thinking of them as simple algebraic expressions, you would have to explain what you mean by p of negative x, which you could do. Or you could simply say it's the linear span of these even powers of x. The sequence space SEQ sub 0 of f of all infinite sequences with finite support is spanned by these particular sequences, E sub k, and we'll use this notation throughout the course. This infinite sequence has a 1 in the kth position and zeros everywhere else. This is another spanning set for this vector space. Notice that this spanning set, for example, does not span the whole sequence space, only the subspace of sequences with finite support, because linear combinations are finite sums. And you can't take a finite sum of vectors like this and get a sequence that does not have finite support. For example, the sequence of all ones is not a linear combination of these sequences. Determining if a vector lies in the span of a finite set, anyway, of vectors often amounts to simply solving a system of linear equations, even though it may be in disguise. Let's look at a couple of examples. Consider these two vectors. They span R2, and we can check that by taking any arbitrary vector in R2, AB, setting up this equation and showing that it has at least one solution. And this is a system of two equations in two unknowns. These two vectors do not span R2. In fact, their linear span, and you could show that in a manner that's similar to what we just talked about. you could set up the equation and show that for some AB there's no solution. But another way to approach this is to just compute the span. That's the set of linear combinations, and they look like this. They're the ordered pairs where the two components are equal. This is, in geometric terms, the 45-degree line through the origin. It's not the whole plane. These three vectors span the subspace of the vector space of all 2 by 2 matrices consisting of just the upper triangular matrices. These three matrices span the vector space of upper triangular matrices. You have to do two things, really. You have to show that this equation always has a solution. This is an arbitrary upper triangular 2 by 2 matrix. But you also have to show that if you stick a non-zero entry here, so the matrix is not upper triangular, there is no solution. And that's quite obvious because you're always going to get a 0 here in the lower left entry. So if you put something non-zero here, there's no solution. Of course, a vector space is a spanning set for itself. So that's pretty useless. But at least it tells us every vector space has a spanning set. But this vector space, for example, the continuous functions on the interval AB, assume that A is less than B, does not seem to have any useful spanning sets because there's no useful set of continuous functions that can capture all continuous functions simply by forming linear combinations, finite sums. Can't do it. The vector space is just too large. Any bases that, any spanning sets that do exist have to be immensely large and intractable, really. So what to do in this situation? Well, that's a bit complicated. One can define special types of vector spaces that have convergence properties, and then rather than represent vectors by finite sums, which is not possible, one can represent vectors by infinite sums, or in other words, infinite series, but they must converge. So one needs a notion of convergence. And that takes us out of the realm of algebra and into the realm of analysis. In particular, one studies Hilbert spaces and Banach spaces and normed spaces in general, where there is a notion of convergence. There's a notion of convergence in the vector spaces we're studying as well, but we're not studying that notion. We're not studying convergence because it belongs to actually an area of mathematics known as functional analysis. So we have to, in a sense here, give up on the notion of spanning set for vector spaces such as this one that are very large. Here's a simple result whose proof I'm going to leave for you. It's good practice dealing with linear combinations. If x and y are subsets of a vector space, then the span of their union is the sum of the spans. While spanning sets provide unambiguous representation for the vectors in their linear span, they do not, in general, provide essential uniqueness, which is the other part of representation that's important. So we need to take a look at when a spanning set for a subspace does provide essentially unique representation and not just arbitrary representation. And I'm going to begin with a term that is not standard, but I like it. I think it's useful. If X is a subset of a vector space V, and if little x belongs to capital X, it may happen that the removal of little x from the set big X does not affect the span. So that would look like this in symbols. The span of X minus little x is the same as the span of X. When this happens, we will refer to little x as span redundant for the set X. The dictionary defines the word redundant as not needed or superfluous, and that fits perfectly. Here's a little theorem. Let X be a non-empty set of vectors in a vector space V. A vector little x in capital X is span redundant for X if and only if little x is a linear combination of the other vectors in capital X. So here's what it looks like in symbols. Little x is span redundant. We don't need it for the span if and only if X is a linear combination of the other vectors in capital X. And that proof of that I'm leaving for you. It's important to note that the span redundancy of a vector, little x, depends on the entire set, capital X. You can't just say a vector span redundant and leave it at that. You've got to say it's span redundant for, and you've got to name the parent set, capital X. For example, here's a set of 3 vectors in R2. Each vector is span redundant in X because you can remove any one of these 3 and it will not change the span. And you have to check that. But if we pull out the vector 1, 1 and we're left with this set, neither vector is span redundant in Y. So these 2 vectors were span redundant in X, but they're not span redundant in Y. This very simple theorem holds the key to finding spanning sets that provide essentially unique representation. For if a set X contains a span redundant vector, little x, then this theorem tells us that little x is a linear combination of the other vectors in capital X. But now we don't have essentially unique representation. Little x itself has 2 representations, at least. X represents itself. It's a very short linear combination with only one term and coefficient 1. but x is also a linear combination of the other vectors in x. So x has at least two representations as linear combinations of vectors in capital X. So we do not have essential uniqueness of representation. Therefore, essentially unique representation implies that there are no span-redundant vectors in the set. Another way to say that is that X is a minimal spanning set. You cannot remove any vectors and maintain the same span. So any proper subset will not span. Therefore, X is a minimal spanning set, and minimal in terms of set inclusion. The converse is also true. A minimal spanning set does provide essentially unique representation, and I'm going to prove that in a few minutes. I want to look at an example or two first. The following two sets of vectors in R3, so we have two vectors here, 1, 0, 0, 1, 1, 0, and three vectors here. They have exactly the same linear span, and you'd have to check that. This is the linear span. It's the set of all ordered triples with the 0 in the third component, in the third coordinate. A here is a minimal spanning set, because if you remove one or the other of these, you are not going to get this full span. B, on the other hand, is not a minimal spanning set, because you can remove any one of the three vectors without affecting the span. And again, that needs to be verified. A set X of vectors in a vector space V provides essentially unique representation for its linear span if and only if X is a minimal spanning set. Or put another way, if and only if X contains no span-redundant vectors. Let me just comment that I said here provides essentially unique representation for its linear span. It can't provide representation, let alone essentially unique representation, for vectors outside the span, because if a vector is not in the span, it's not a linear combination at all. Okay, so I probably didn't even need to say that, but it's better, it's clearer to do so. Now we've seen that spanning sets that do provide essentially unique representation must be minimal. We just did that. So it's the converse we need to discuss now. We need to show that if X is a minimal spanning set for its span, which I'll call S, then X provides essentially unique representation, which means that no vector in S can have two non-equivalent expressions as linear combinations of the vectors in X. So if V, this non-zero vector, if V is non-zero, and if it has this expression where the x's are in X, capital X, and it also has this expression where the y's are also in capital X, and if the coefficients are non-zero. We've eliminated any zero terms. And the x's are distinct, so we've combined any like terms. And the y's are distinct, so they're also combined any like terms. Then what we need to show is that these are the same, so that n equals m, and that each a is a b. All right, so this is what we're going to do. We're going to this is the linear combination here, and we'll subtract from it this linear combination. So we're going to get 0. I'd like to, some of the x's may equal a y. That's certainly possible. The x's are distinct, the y's are distinct, but we don't know whether the x's are equal to the y's. That's what we're trying to show. But by re-indexing the y's, changing the indices, we can assume that x1 equals y1 all the way up to xk equals yk, but after that, they're all different. So there are no more equalities among the little x's and the little y's. Okay. K could be 0. There might not be any, but k, we don't know. Okay. Well, then we can regroup here so that 0 equals a1 minus b1 times x1 through ak minus bk times xk plus the additional x's that are not involved in these equalities minus the additional y terms that are not involved. Probably would have been better to put square brackets here, so I think I'll change that. Okay, so it now looks, the equation now looks like this. Well, if there are any terms in this square bracket that are non-zero, we could move one of those terms to the other side of the equal sign, which would show that, say, one of these x's is in the linear span of the other vectors, and they are vectors from capital X different from the little x we moved over. Okay? And so we lack span, we have a span redundancy. Okay? And so this is not a minimal, X is not a minimal spanning set, which is false. We're assuming it is. If there's a y term over here, we can do the same thing. We can move it to the other side, get y, that y term expressed as a linear combination of other vectors in capital X. That y vector is then span redundant, contradicting the minimality of X as a spanning set. So there are no vectors here, and there are no vectors here. 0 equals just the vectors in this first pair of brackets. But then if one of these terms in this bracket, in this set of brackets, is non-zero, at least two of them have to be non-zero, and we can do the same thing we did earlier. Move one to the other side, express it as a linear combination of the other x vectors, again a contradiction to the minimality of X as a spanning set. This is really a very simple argument that looks a lot worse than it is, partly because of the long equations and the words that are necessary to explain it. All we're doing is saying if you have something that looks like this under certain conditions, which we do have, then unless these are identical after reordering of terms, there's going to be a span redundant vector. There's going to be a vector here somewhere that's a linear combination of the other vectors. Let's look at this set here of two vectors in R3. We've seen it before. This is a minimal spanning set, and therefore, according to the theorem we just proved, it provides essentially unique representation for every vector in its span. Remember, those were the ordered triples where there was a 0 in the third coordinate. Every vector with that property, every vector in R3 with the 0 in the third coordinate, is a linear combination of these two, and that linear combination is essentially unique. Okay, we have exactly what we want for that subspace. Essentially unique, as close to unique as possible, representation or identification of every vector in the subspace using just two vectors. There's infinitely many vectors in that subspace. All we need are two vectors to give unique, essentially unique, identification of every vector in that infinite subspace. And that is our goal. This set of vectors, even though it's bigger, 3 vectors, does not provide essentially unique representation. And here's an example. This vector is represented by itself because it's in Y, but it's also represented by this linear combination of these two vectors from Y. This vector is span redundant, this third vector. So this subspace, this set has at least one span redundant vector and therefore does not provide unique, essentially unique representation. This theorem that we just proved tells us that it is precisely the minimal spanning sets that provide essentially unique representation of vectors in its span. So minimal spanning sets are the desirable spanning sets. They're more efficient. They don't waste resources by identifying a vector using two different, essentially different linear combinations. It's like having a credit card account with multiple credit card numbers assigned to it. It's a waste of resources. How would you like it if you were a student at the university and you had 50,000 student IDs? It's ridiculous. Or infinitely many student IDs. That is inefficient. So, how do we tell which spanning sets are minimal spanning sets? And before I answer that question, there is something a little funny about the question. Every set is a spanning set. It's a spanning set for its span, just to be clear on that. So it probably would have been better to say, how does one tell which sets are minimal spanning sets? Maybe you should email me and tell me if I should take the word spanning out here. I put it in because I wanted it to be clear without any possible confusion what I'm talking about. But it is redundant, if you'll excuse that use of the term. It's not necessary. Every set is a spanning set for its linear span. The fact, of course, that we've just proven that minimal spanning sets can be characterized as those spanning sets that provide essentially unique representation is far from a practical way to determine minimality. It describes the reason that minimality is important, but it's not very useful for determining minimality. But the next theorem tells us that all we need to do to check for a minimal spanning set, or in other words for a set that has essentially unique representation, is check to see if the zero vector has an essentially unique representation. And this is a consequence of the properties of linearity. So this argument works for vector spaces and modules, which are very similar to vector spaces. It doesn't work for groups, it doesn't work for rings, it doesn't work for fields. It's the linearity that makes this work. And that, of course, is a much simpler test. Can you write 0 as a non-trivial linear combination? If you can, you have redundancy. The 0 vector has two different representations. And therefore, as we'll see in the next theorem, all vectors have more than one representation, essentially different representation. Okay, here is the theorem. A non-empty set X of vectors in a vector space V provides essentially unique representation and is therefore a minimal spanning set if and only if the 0 vector has an essentially unique representation as a linear combination of vectors in X. Well, on the one hand, of course, essentially unique representation would include the case of the 0 vector. So one direction of this biconditional is sort of obvious. The other direction is the important one. If 0 has an essentially unique representation, does every vector have an essentially unique representation? Well, suppose we have a non-zero vector V, I should put that in here, that has two representations. Linear combination of x's, linear combination of y's, both equal to V. This proof, by the way, is very similar to the one we just did. And here we assume all the coefficients are non-zero, so we've eliminated 0 terms. The x's are distinct, the y's are distinct. Again, we move everything to one side, so I can again do the square brackets here. And by re-indexing again, if necessary, we match some x's. We match the x's with the y's that are matchable, and we gather the terms like this. So this is what we did before in the previous proof. But we can stop here, or we couldn't stop before, because now we have 0 as two different representations, 0 itself and this mess here, unless there are none of these and none of these, which means n is equal to k and m is equal to k. So n and m are equal. And so these go away, and then all that's left is this, but this has to go away. And since the x's are non-zero, the only way this can go away is if the a's are equal to the b's. So after reordering, if necessary, the b's, or reindexing, we get the same, we get identical expressions. Now there's some very famous terminology surrounding the concept of essentially unique representation of the zero vector, which, as we just got through showing, is all you need to prove that a set is a minimal spanning set and uniquely represents all vectors in its span. So X is a non-empty set of vectors in a vector space V. X is linearly independent if the zero vector has an essentially unique representation in the span of X. And that is to say that if you have distinct vectors in capital X, if a linear combination of those vectors is equal to 0, then the coefficients have to be 0, so you don't get two different representations of 0. Any equation of this form, where the x's are distinct, it's meaningless if the x's don't have to be distinct, because you could have little x minus little x, and that's always equal to 0. So we have to assume the x's are distinct, and not all of the coefficients are 0. This is called a linear dependency among these vectors, or just in the set capital X. If capital X has a linear dependency, then it's said to be linearly dependent. Okay. Now, I will pause here to say that this discussion, this entire video, basically, up to this point, where we finally defined linear independence, is quite different from what you will see in books, in other books, and probably in other classes. The typical approach is simply to define linear independence, and this is the definition at the beginning of the lecture. And in my experience, students always, well, some don't understand it, some understand it but don't understand why we're even making the definition, because the idea of essentially unique representation is not really explained as the motivation behind all of this. The motivation behind spanning sets and linearly independent sets, and therefore bases, is to get essentially unique representation of all the vectors in a vector space. Hopefully by a finite set, but that doesn't always work out. For Rn it does, for matrices it does, but for polynomials you need an infinite set to represent all the polynomials uniquely. Showing that a set of vectors is linearly dependent involves showing that a certain homogeneous system, that's equals 0 here, has only the trivial solution. Or has no non-trivial solutions, the same thing. Here are some examples. Any set of vectors that contains the 0 vector is going to be linearly dependent. We always have this rather trivial dependency. Any non-zero scalar times the zero vector will equal 0. So we have a very short linear dependency. Referring to a previous example, 1.56, these three vectors are linearly dependent because the homogeneous system, right here, a times the first vector plus b times the second plus c times the third equals 0, has a non-trivial solution. So these three vectors are linearly dependent. There is a linear dependency among these three vectors. This is what the dependency actually looks like. On the other hand, these three vectors are linearly independent because this equation, similar to this one, has only the trivial solution. So there is no linear dependency among these three vectors, and therefore they are linearly independent. For the vector space of 2 by 2 matrices over a field F, these three matrices are linearly independent because this equation, which is really a system of four equations in four unknowns, a homogeneous system, has only the trivial solution, which I'll let you verify. In the polynomial space, these three polynomials are linearly dependent because this system of equations, this is three equations in three unknowns, has a non-trivial solution, and that gives a linear dependency. Here's a little theorem whose proof I'm leaving to you. V is a vector space, X is a subset of V. If X is linearly independent, then so is any non-empty subset of X. If there's no linear dependencies among X, there can't be any linear dependencies among the vectors in a subset of X. You just have to find a formal way to write that down. If X is linearly dependent, then so is any superset of X. Well, now we can incorporate the notion of linear independence into our previous discussion. There is one little wrinkle, and that is with the zero vector. The presence of the zero vector destroys linear independence, as we've seen in an example. It also destroys the minimality of spanning sets. Spanning set with a zero vector in it can't be minimal. But it doesn't have any effect on essentially unique representation because of the word essentially. So here's the statement of the theorem, and I had to say let X be a non-empty set of non-zero vectors, specifically non-zero vectors in a vector space. Then the following are equivalent. X is linearly independent, and so provides essentially unique representation for the zero vector. That's what this means, really, linear independence. X provides essentially unique representation for all vectors, and X is a minimal spanning set for its span. And the proof is just basically, you can see it's one line here, it's just collecting previous results together. One last item on linear independence. Theorem 1.64 tells us that we can always remove vectors from a linearly independent set and retain linear independence. But sometimes we would like to include a vector in an independent set, and we want to know whether the new set is still linearly independent. That's harder to do. You can't just throw in anything you want. For example, if the two vectors x and y are linearly independent and you toss in x plus y, you now have a linear dependency in this set, and you've lost linear independence. But you can add or include a vector. You've got to be careful not to use the word add, because we've got addition here in a vector space, so we're not literally adding, we're including. If I is a linearly independent subset of a vector space V, and little v is a vector that's not in I, then we can include V in the set I, get a bigger set. It will be linearly independent if and only if V, the little vector V, is not in the span of the vectors in I. In other words, we can throw in a new vector to an independent set and preserve independence, provided the new vector was not a linear combination of what we already had. Another part to this theorem that we will use later, the union of a chain of linearly independent subsets is linearly independent. We had a theorem some time ago that the union of a chain of subspaces is a subspace, unlike arbitrary unions of subspaces. This tells us that if the subspaces are linearly independent, so is their union, as long as the family is a chain.